Okay, so this is the mass on a spring project. Make sure you have watched this lecture video before you even start on this project. Like, I basically cover all the basics of mass on a spring as a regular lecture video. So you can't just do that. That's not project worthy. We're going to take that up a notch. But this will give you all the basics here. So this is a great, I'll show you how I got here. This is a great source. I just Googled mass on a spring differential equation example, and it's this place here. It's a great source. We're going to change a little something from what they do here. They have their mass oscillating vertically. I don't want to have to deal with all this stuff at the beginning with finding the new spring constant and all that. We're going to have our mass horizontal. Everything else will be the same. So just quickly, we're going to have some spring here, some mass that's oscillating back and forth. So if we say this is x equals 0 here, and we've stretched out to some position x, then Hooke's law says that there's a restoring force, let's call it Fs for spring, is negative Kx. Okay, so we could just, write down Newton's second law, F equals ma. That's our only force. We could solve, we get sines and cosines. It's a boring problem. We're going to throw in a dampening force. So if I draw a free body diagram here, at this moment in time, my restoring force, Hooke's law, is pushing me back to the left. The dampening force, let's call it maybe FD for dampening, is proportional to your velocity and points in the opposite direction of velocity. So if you're moving to the left, it would push to the right. So this is negative some beta V. So that would push back this way. So in your presentation, you're going to quickly go through this. Don't spend a lot of time on it. Draw some pictures, or if you do go out, like you could just Google mass on a spring and you could find some professionally made image that looks like this, but make sure you cite your source. Like at that moment, if you put an image in your paper, right there underneath the image, tell us where you got it from. And we need a free body diagram. It's perfectly fine to hand draw these. If we were publishing a paper, yes, these would need to be professionally done. It's okay to hand draw these and just, save it as a PNG or a GIF or whatever, a JPEG. Throw it in your paper. You got to have both. You got to have an image. You got to have a free body diagram. Okay, then recall V is just the derivative. Velocity is the derivative of position. So then F equals ma, or sum of the forces, equals mass times acceleration. But acceleration is just the second derivative of position. So this would be negative beta x prime minus kx. Literally everything here I go through in that lecture video, and I go through all the basic cases when we have overdamped, underdamped, and critically damped. So we don't need to re-walk through all that. You may mention here, recall that the professor went through all this before. You're just refreshing people's memories. We put this in like standard form, mx double prime plus beta x prime plus kx equals 0. Here's our dE. And like here, even in this source here, we get underdamped. Trying to get back to him. So here's our DE. It's a second order linear homogeneous with constant coefficients. Make sure you mention that. The solutions to the characteristic polynomial, just using quadratic formula, we get this. And we get underdamped if the discriminant here is negative. So again, we're maybe 2 minutes into your actual presentation, and you've quickly re-walked us through all that and say, okay, we're going to be doing an example here where we're underdamped, where we have something of this form. And let's use the numbers that they have here. And I don't want to deal with all the stuff, all this weird stuff they've got there. We're going to use the following numbers because then our solution's right in front of us. Okay, so we're going to use a mass of 1/2 of a kilogram. Beta, I think, is 1 and K is 5. What were the numbers again? 1 and 5. Yes. This is newtons per meter. I can never remember. I got to think about what units B has. So it should be newtons times seconds per meter, because then when I multiply by meters per second, yeah, so newton seconds per meter. When I multiply by meters per second, I end up with newtons. Okay, so we're going to use these numbers and solve the DE. Okay, nothing too difficult here. Overall, this is a pretty easy project. It's one of the easier projects you could choose. This is only part one. We're going to make it a little more challenging in a minute because like the solution's right here. But you're going to walk us through the steps. In the paper, you got to show all of the details. Here, we can use their same initial conditions even. We could say x of 0 was, would they have 3/4 meters, and x prime of 0 was 0 meters per second. Let me make sure I got that right. Yeah. So solve the DE. In the paper, go through all the boring details. You get your characteristic polynomial, get your solutions, write up your general or your solve the IVP. During the presentation, don't bore us to death with all the boring details. Just hit the highlights. Okay. Now we get into part 2. And we're going to do forced oscillations. So we're going to throw in a forcing function. So we're going to have some f that's a function of t. Let's do a cosine. So maybe like, what kind of numbers do I want here? Let me pause and look at what group did last. Okay, let's say maybe 2 sine of, we want a similar kind of period here. We're going to talk about resonance in a minute, maybe 6t. Okay, so now we're going to have a non-homogeneous DE. And it'll be m x double prime plus beta x prime plus kx equals this forcing function. So this will be on the other side. So you're going to have to solve this as a non-homogeneous DE. You've already solved your homogeneous version. We're going to use the same M, beta, and K. Then you have to find use undetermined coefficients to find your particular solution, squish it all together. So solve this. Again, in the paper, you're going to walk us through all the boring details, show all the steps, but then during the presentation, just hit the highlights. We're going to assume F here has the form A sine plus B cosine. Just show the highlights. Don't don't read a bunch of math to us. In fact, remember, the number one rule of your presentation is do not read to your audience. I'm going to say that over and over again. Do not read. Don't read words or math to your audience, but solve the DE. Same initial conditions. You remember when you're doing this, up here, you use these initial conditions as soon as you got your characteristic polynomial, you get your C1, your C2, then you plugged in your initial conditions. When you're solving a non-homogeneous, you got to get your particular solution first. The very last thing you do is get your C1 and your C2. You cannot reuse the C1 and C2 from up here. Oh, I should say here. Once you solve this guy, graph him. And then discuss the graph. The entire point of having a graph is to discuss it. So you'll draw a nice pretty graph. Make sure we can clearly see the oscillations. Adjust your window. I would use Desmos to make the graph. Make sure you label your axes. Maybe show us what the period is. Show enough oscillations so that we can see the dampening, that our amplitudes are decreasing as we go. So you'll write a couple of sentences in your paper describing what we see in that picture. The whole point of having a graph is to give you something to talk about. Once we get down here, again, solve and graph, talk about the graph. Okay, then real world examples. So this part you're going to have a lot more leeway on. I want you to discuss real world examples of forced oscillations, dampening, resonance. These are the phrases that you want to be using. A classic example that pretty much every group that does this project discusses is the Tacoma Bridge. Here we can see the video. You could show this.
There's DIY.
Sorry.
And there's doing it yourself.
During your actual presentation, it's okay to pull up this video and just show a snippet of it. I wouldn't show more than 10 or 20 seconds. But watch this. Look at that bridge. This is because of forced oscillations and resonance. I don't remember all the details. You'll want to Google the details if you're going to talk about this during your presentation. But I believe the wind was blowing at just the right frequency and was catching parts of the bridge at the bridge's resonant frequency so that the wind was pumping energy into the system. Imagine like a kid on the swing, you're swinging. You know how if you lean back at just the right moment when you're swinging on a swing set, it adds energy in. And then when you're near the top, you lean forward and it adds energy in. And that's how you get going higher and higher. That's because you're pumping in energy at the correct frequency, at the resonant frequency of your swinging. That's what was happening here. So this is a great example. Use this. You can also discuss how buildings are built with dampening systems for earthquake protection. So Google that. Pick two or three interesting real world examples of forced vibrations, resonance, and dampening, and discuss those in your paper and in your presentation. Your entire presentation should be 10 to 15 minutes long, and I would rather have 9.5 minutes than 15.5 minutes. Never ever go over your allotted time. If you were at a conference and you were presenting and they said you got 15 minutes to present and you went 16 minutes, they would never invite you back again. Never go over your allotted time. It's better to be a little bit short. Do not read to your audience. You're going to have every single detail in the paper. The presentation is just the highlights. You're just hitting the big interesting parts, but you're not going to read to the audience. Sometimes people will have note cards while they're presenting, and you can't see the words on the screen, but you can hear them reading. You'll hear, like, here's another group's paper on this project. And on the screen, maybe they'll have a picture, but then you'll hear force damped is when an external force acts on the system. Basically, you are applying an eternal force that puts energy into the system at a certain frequency, not necessarily the same as the natural. Oh my God, it's so boring. You're already bored right now. Do not do that. You're going to be graded as a group, how the entire paper, slideshow presentation, you can be graded on it. Is it complete, accurate, the whole works? And then you're going to be graded individually on your own presentation style. And I promise you, my number one pet peeve is people reading to the audience. Do not read to the audience. Don't read math or words. You're never, ever, ever going to have a whole big chunk of text or math on the screen at one time. Like as I'm talking right now, some of you are trying to read all these words on the screen. You're ignoring me because you're trying to read this. If you put words in front of people, they're going to read them. Don't do that. Don't put a bunch of math. Like, let's say I had all this on the screen at one time. That people aren't listening to you. They're trying to read all this. Never have more than like one or two equations on a screen at the same time, and don't read the math to us. You've got whoever's presenting needs to have control of the slideshow so that you have access to the mouse. And then you're going to point to stuff. You would never, ever just go R equals -4/2 plus or minus 16 minus 80 over 2. R equals -2 plus. If you read all this math to us, you're going to run over and you're going to bore your audience to death. Like here, say I was trying to show how we would solve for our constants. Here's our DE, there's C1 and C2. Plugging in all of our initial conditions, we get C1 equals 3/4. And then you could see our paper for all the details, but solving the system, x prime of 0 equals 0. So we get C2 equals 3/8. And here's our final solution. Something along those lines. Obviously, you're going to have different numbers. You wouldn't have all this math on the screen. It would all be in the paper, but you're just going to hit the highlights, point to stuff, and everybody in the class should understand, oh, okay, I know the procedure. I could follow along with what's going on without being bored to death. Again, you're going to have, like, I would have a better looking graph. Like, make sure we can actually see the oscillations. This is way too zoomed in or zoomed out. You'd want to be zoomed in a lot more. Don't read to your audience. Okay, so you're going to type up a paper that has all the details, and you're going to copy stuff into a slideshow. How do you type up the paper? My recommendation is to use Google Docs so that everyone has access. Everybody here should know how to use Google Docs. Then I highly recommend you install this extension called Auto LaTeX Equations. Everybody in the class is probably an engineering major. You're going to have to learn LaTeX at some point anyways. Now's a good time to get started. So we just type. To type math, we're just going to type it out, and all of our math needs to be enclosed in these dollar signs. So I might type, I don't know, the differential equation is, and then double dollar signs, mx double prime plus, what do I call it? Beta. So beta, I would get like this, x prime plus kx equals 0. Say we're doing part one version. And then hit render equation. That produces a nice, beautiful image. You may have to Google how to do some stuff in LaTeX, but that's part of this learning process. So type up the entire paper before you start working on the slideshow. That's my recommendation. Then I would recommend using Google Slides so that everybody has access to it. And you can type math here in Google Slides. There are even extensions. But why reinvent the wheel? We've already typed up all the math. My recommendation is type up the paper first, and then whatever goes in the slideshow, just highlight it, Control C, come over here, Control V, boom, you're done. Move it around, resize it. Remember, the paper has all the details. The slideshow is just the highlights. It's better to have multiple slides with just one or two, pieces of math each than a whole bunch of stuff on one slide. Now, I know you guys love making fancy presentations with all the transitions and the backgrounds, and I'm going to tell you, I could not care less about any of that. Like your entire presentation could be white backgrounds with just text and math, and I'm perfectly fine. If you want to spend the time making the presentation look fancy, go right ahead, but it ain't going to earn you any extra points. I'm going to grade you on the content. Okay, so my recommendation is probably have one person write up all the math, like by hand, paper and pencil. Share it with everyone, have everyone check. Have somebody type up the paper. Then once that's done, have somebody create the slideshow and produce all the graphs. And that's if you got 3 people. If you got 4 people, you have to adjust that a little bit. But everybody is responsible for the entire thing. Do not think, oh, I'll do part one and I'm fully responsible for that. And then Dave over here is going to do part two with the force vibrations, and Joe's going to do all the real world applications. And like sometimes people do that, and then each part of the paper looks different. It, the typesetting is different. The like the mood is different. I don't know what word I'm looking for here. It reads like 3 different papers or 4 different papers or whatever squished together, and it's terrible. Make sure everything is consistent. Everybody's responsible for the entire project. So it is your job to go through and check everybody else. We're going to talk later about what do you do if somebody's not pulling their weight. I'm going to spend a lot of time talking to the whole class about that. Don't stress about that at the moment. Like we'll deal with that. But everybody's responsible for the whole thing. When you go to present, everybody must present You're graded on the entire presentation, and then you're also graded individually on your own presentation. Does it sound like you know what you're talking about? Are you reading to the audience? Those are the most important things. If you read to the audience, you're going to get a terrible score. Okay. I think that should cover everything. It's a good place to stop.